Hello, beta. Welcome back to my YouTube channel. So, one second. Am I audible and visible to all of you? Hello, beta. Hello, Asna. Am I audible and visible to all of you? Yes. Am I audible and visible to all of you? Hello, beta. Yeah. So, as you know that today we will be having second last lecture of magnetism. Okay. We will and basically is yeah every day timing is same. Okay, 10:30 p.m. every day. Okay. So basically, today we will be discussing second last lecture. So in which, in this particular lecture, we will be starting magnetism. And I guess you have seen the EMI lecture series also coming from Friday. We will be having EMI. Okay. Okay. So let's start the lecture now without any delay. Okay. So let us start with the lecture. I think lecture number 9. No? I guess this one is lecture number 9. Okay, first of all, I need to see whether the transition is on and off. Then we will start. Okay, so it is visible. So let us start lecture number 9. Lecture 9, and this one is second last lecture. Second last lecture. Okay, so let's start the lecture with a numerical. I have just added some numericals here. Okay, so first numerical. Okay, and this numerical is based from the last topic that we have studied. Shahid Ali. Hello, beta Shahid Ali. Yeah, I'm great. Okay, so let's start now. As you can see, what we are having, no? So we are having a short bar magnetic placed with its axis at 30 degree with a uniform external magnetic field. So what is given to us? Sir, theta is 30 degree and magnetic field B is given as 0.25 Tesla. Done. Experiences a torque of magnitude equal to this much. So we are having what? Torque. So torque is also given us and it is 4.5, 10 to power minus 2 joules. What is the magnitude of magnetic movement of the magnet? So what we have to find out? We need to find magnetic movement magnitude. So as we know that magnetic movement, no? So what is the formula for magnetic movement? Any idea? Huh? If it is bar magnet, so I can use m into 2l, now the length of it. But you can see here, no? Torque is given. B is given, theta is given. I guess something related to this formula we have it, no? Which formula? Torque. What is torque now? I guess my torque is m cross b, or I can write torque equals to mb sine theta. Done. What is torque? Tau. It is 4.5, 4.5 10 to the power minus 2. M, we need to find this m. And b, what is b? It is 0.25 Tesla. Then we are having sine 30, no? Sine 30 degree. So I can write here 0.5 10 to power minus 2 equals to m. It is 0.25 and sine 30 is 1 by 2. Therefore, my m came out to be 4.5 into 10 to power minus 2 multiplied by 2 whole divided by 0.25. Cancel out. Here I have here 100, 25 1, 25 4. So I can write it is, look, 4 to the 8, 4 to the 20, 20, 18, it's 18.0 multiplied by 2, 10 to power minus 2. 36, 10 to power minus 2. Is it 0.36? So my answer came out to be 0.36. Easy or super easy? Huh? Am I lagging? One second, am I lagging? No. Okay. I guess this numerical is pretty easy. Right now? Okay. Look now, one more numerical. So one more numerical from short magnetic things. So look, what are the things given to us? A short bar magnet of it is magnetic moment is capital M, right? It's capital M. It is given as 0.32 joule per Tesla. Is placed in a uniform magnetic field of 0.15 Tesla. If the bar magnet is free to rotate in a plane of the field, which orientation would correspond to its stable? Stable. Second is unstable equilibrium. What is the potential energy of the magnet in each case? Okay. So what are the things given to us? Sir, I guess magnetic moment M, it is given to us, it is 0.32 joule per Tesla. Then B is given to us, it is 0.15 Tesla. And my magnet is free to rotate. I need to find out at what particular orientation it would be a stable equilibrium. I guess we know that stable means when theta is 0 degree, and unstable simply indicates when my theta equals to 180 degree. Done. When my theta is 0 degree, it is stable. When theta is 180, it is unstable. We know it. Hello, beta. Sri Jan Singh Chauhan, hello. Look now. So for potential energy U, do you know what is U? I guess U is nothing. It is minus mb sine theta. No, it is minus mb cos theta. Why? Because U here is a scalar quantity, na? M dot B. Okay. So in each case simply indicates when my system is in stable equilibrium. That means when theta is 0 degree. Second part, when my system is at unstable equilibrium. That means when my theta is 180 degree. So my U came out to be, it is minus M. M is 0.32, 32. B is 0.15. And we're having cos 0 degree. Second one, U came out to be minus 0.32, 0.15, cos 180 degree. Okay, U. Cos 0 is plus 1. 0.32 multiplied by 0.15. Okay, so we need to do it is calculation. 0.32 multiplied by 0.15. So we can write it is 32 multiplied by 15. 5 to 10, 15, 16, 32, 0, 8, 4. We're having 2. This answer is coming out to be 0.080, right? Yes, so it is minus 0.048. Here, U. This quantity is same. But cos 180 is plus 1. So I can write it is plus 0.048. Done. So we know that minimum potential energy means stable, maximum means unstable. So this is the answer of my numerical. Easy or super easy? Done. Now let us start with the dipole things. So let us recap one thing. Let us recap electric dipole concept. Electric dipole concept from electrostatics. If this is my minus q charge, here we have plus q charge. Between minus q and plus q, if we are having a length, usually we are taking 12 lengths, right? Usually we are taking 12 lengths. We can take L also, there is no issue. And if we extend this line, so this line means axial line. This is axial line. And if you want to find electric field intensity on the axial line of a dipole, due to this positive, it would be in this way, E positive. Due to negative, it will be in this way, E negative. Okay. And at the end, we are getting E net. This is my E net now, after deriving it. And E net came out to be 2kp by r cube. I guess you know this relation from electric dipole, no? That means when theta is 0 degree and p is in this way, no? When theta equals to 0 degree, it simply indicates it is axial position. Axial. For axial position, my E, electric field intensity, is 2kp by r cube. And if we are deriving it for equatorial position, this is my equatorial position. Look now. Okay. So here we are getting E equatorial. This is my E equatorial, which is opposite to my P, electric dipole, right? Moment. It is kp by r cube. Here angle theta is equal to 180 degree. I guess we know this thing very well. Right? Similarly, if we are dealing it with a magnet, no? If we are having a magnet, okay, south pole, north pole, minus m, pole strength plus m, length is L. So if we just increase this particular side, okay, look, we know that magnetic moment is from, it is my magnetic moment direction now, from minus m to plus m. Now here, if you want to find it is magnet B axial, that means when theta equals to 0 degree between magnetic moment and magnetic field, it came out to be, look, 2 is 2. What is k? Sir, k is constant, that it is 1 over 4 pi epsilon naught. Here the constant is nu naught by 4 pi. Same. We are having p. In this case, we are having m. R same. It is r cube. If we are talking about the equatorial position, this is my equatorial position. Okay. So this would be my answer. This point is my B equatorial. Theta equals to 180 degree. Same. It is kp by r cube. K means nu naught by 4 pi. P means m by r cube. So you need to remember this formula, this and this one. Okay. So we don't need to memorize each and every formula. No? It is very hard to us. So then how we can do the calculational part? Just memorize the way of deriving formula once. That means how we are deriving it in electrostatic, in the same way we can derive it here. So why utilizing our energy multiple times? No? At then we are getting the same formula with little bit of manipulation only. There torque na P cross E, here M cross B. Okay, so we don't need to just do all these things, no? Then it is very hard to memorize 1,000 formulas. Remember a couple of formulas, and then from those formulas you can just manipulate your own formula based on the requirement of the numericals. Done? Okay. So let us do a numerical. If you are just good enough with these things now, let us start the numerical part now. Okay, one numerical. Not a very big one, a small numerical. And my numerical looks like we are having a bar magnet with magnetic moment is given as 0.48 joule per Tesla. And the R is given as 10 centimeter. I guess 10 centimeter, I can write it equals to 10 multiplied by 10 to power minus 2 meter, which is equals to 10 to the power minus 1 meter. Okay. So basically the R is given to us, this one. And my M is given to us, it is this one. Okay. Now what is being asked to us? Ayush, as of now, no, only one examination. As of now. I don't know, no? Look now. So first of all, let us find B axial. What is B axial? 2 Kp by R cube, nu naught by 4 pi, M by R cube. 2 is 2. What is nu naught? Nu naught is, I guess, 4 pi 10 to power minus 7 whole divided by 4 pi. What is M? M is 0.48 divided by 10 to power minus 1 cube. So look now, 4 pi cancel out. Then what we're having? It is 0.48 multiplied by 2. 8 to are 16, it is 16. 4 to the 8, 9, it is 0.96. 10 to power minus 7 divided by 10 to power minus 3. Let us take this thing up, it will become positive. So I am having here 0.96, 10 to power minus 7 plus 3, which ultimately becomes 0.96, 10 to power minus 4 Tesla. And one thing that is one, do you have any? No, beta, I don't have any paid batch on YouTube now. I am working with some edtech, so there you can have it. Okay. So, okay. So as we know that one Gauss equals to 10 to power minus 4 Tesla. So I guess we can just take this thing out now. So I can write 0.96 is Gauss. Okay. 0.96 is Gauss. Okay. So B axial N, now we are having B equatorial, right? We're having B equatorial. I guess that thing is nu naught upon 4 pi M by R cube. Yes, sir. It is 4 pi 10 to power minus 7 divided by 4 pi. What is M? M is, I guess, 0.48 divided by 10 to power minus 1 cube. 4 pi cancel out. So I guess we are having 0.48 multiplied by 10 to power minus 7 divided by 10 to power minus 3. Let us take this thing up. So we are having now 0.48 10 to power minus 7 plus 3. It will become here 0.48 10 to power minus 4. So this thing I can use Gauss here. So I can write 0.48 Gauss. Easy or super easy? Easy or super easy? Huh? Super easy, no? Okay, let us do a numerical, a unique one. Okay, let's do a numerical, a unique one. Unique one. Okay. So how unique one? Let's suppose we are having a magnetic movement now. Look, one thing. Okay. So now center, let us divide it in this way. A unique approach with a unit numericals, right? Now we are having a magnetic moment. This line represents my magnetic moment. M. Okay, done. Look here, this particular point. So what does this particular point represents? Sir, this particular point represents, it should be an axial point. This is my axial point or axial position. How? Because, hello beta, one second beta. Oh, today we are having lot of members, right? One second, I need to remove these members, then we will start class. Once again, one second. So now I don't know this Nikhil Prata. Okay. So Thakur YT, I don't know it is member or not. One second. So just for, okay, this one is also done. I guess Thakur is also spammer coming now. One second. Is there anyone left? Nikita is here. One second, beta. I'm just removing these idiots from my lecture so that. Hello, beta. So let us just give me 1 minute so that I will just have it. I don't know why these are people coming in my channel, right? One second. I guess no member left, no? Yeah, very good evening. I guess we don't have any member now. Let's just continue our session. Okay, look. Axial position means at particular position where my theta is 0 degree with a magnetic movement. Look here. Here my theta is 0, so you can write the magnetic field at this particular direction would be in this way. B1, let's suppose B1. Okay, thank you, beta. Now this particular position, sir, this one is also a axial position. So I can write B2, suppose, no? Now, these are perpendicular to my magnetic movement. So these particular positions are known as equatorial position. These known as equatorial position. And at equatorial position, my theta is 180 degree between M and B. So my B will be in this way. Okay, one second. B now, my B will be in this way. Look now. B3. My B4 here, it will be in this way. Done? Now, look now. If we are having a dipole, different one, place it here. Look now. In this manner. In these manners, right? Look. Suppose, look here. One, second, third, fourth, fifth, sixth. Now comment which one will be stable equilibrium and which one will be at unstable equilibrium. Look here. I guess here, if you can see now, B and M. This is B, this is M now. I guess you can see here theta is 0 degree between these two. Between these two, theta is 0. Okay. Here, my B is upwards and M is downwards. So if you talk about these two, my theta came out to be 180 degree. If we talk about these two, these are opposite to each other. Theta is 180 degree. If we talk about these two, my theta came 0 degree. Look here, these everything in any point on this particular line represents equatorial position. So my B will be in this way. B 90 degree. 90 degrees. So these 2 point positions, no equilibrium at all. For stable, theta is 0 degree. For unstable, theta is 180 degree. So now I guess you can comment now. This one is unstable. Unstable. This one is stable. This one is stable. This one is stable. This one is unstable. These two are not in any equilibrium. Done? Clear now? Okay. So now if we want to study if this is stable, this one is also stable. Which one is having minimum potential energy? Minimum potential energy. Okay. Look now. One thing that you need to remember now, minus 100 or minus 50. Which one would be a minimum value? Which one is minimum value? If you need to comment on minus 100 is minimum or minus 50 is minimum. So you will write, sir, minus 100 is minimum. This one is minimum, right? Look now. This one is my axial position. So value is 2 nu naught by 4 pi m by r cube. And this one is nu naught by 4 pi m by r cube. I guess this one is more. This one is more as compared to this one. So you can write this one is more stable. More stable. Okay. Or you can write minimum potential energy will be at this axial position. Done? Done, no? Okay. Take a 1 minute rest. So now we will start something different. Clear now? One second. Okay. So let us start Gauss's law of magnetism. Start Gauss's law of magnetism. Gauss's law of magnetism. And what we know from the electrostatic, Gauss's law states that the net flux through any closed Gaussian loop equals to charge enclosed by that loop divided by the epsilon naught. Okay, we know it very well. Or you can write, sir, Gaussian, that is flux equals to integration of E dot dA equals to Q enclosed by epsilon naught. This one is Gauss's law in electrostatics. This one is Gauss's law in electrostatics. Now, Gauss's law of magnetism indicates that net magnetic flux through any closed loop is zero. First point. Second point is magnetic monopole doesn't exist. Simply indicates that if we are having magnetic flux means magnetic lines, and you know that magnetic lines is always a closed loop. If these are my magnetic lines, right? Closed loop, we know it. Let's suppose it is in this way. It is going in this way. Then, if we want to study any part, let us talk about this part. If we want this part, okay. So find flux through this particular part. Flux means incoming, outgoing. So how many lines are going inwards? Sir, two lines. Incoming flux is 2. How many flux are going? Sir, 2 flux are going. So incoming, so you can write incoming lines equals to outgoing. On and always. What? Always why? Because these are in closed loops. Magnetic lines are always in closed loops, right? Incoming equals to outgoing. So it simply indicates the magnetic field through any closed loop equals to 0. This is a statement of Gauss's law of magnetism. Very simple, very easy. Clear? One second, beta. Easy now? Very easy. Okay. Now let's start Next topic known as moving coil galvanometer. Okay, what we're having? Moving coil galvanometer. Moving coil galvanometer. Moving coil galvanometer. So it is something like this. Look. Okay. Let's suppose I current goes inside your magnetic this kind of loop. Suppose I current flows through this loop. Done. If current I is flowing through any loop, so what will happen then? One more thing is there, that is this loop. These magnets, no? These magnets. These are cylindrical magnets. These are not ordinary one. These are cylindrical magnets. Cylindrical. So the use of cylindrical magnets is there, that they are giving this magnetic lines at a 90-degree angle only. Okay, every line is making 90 degree with the surface of this coil. Surface of this coil, 90 degree. Okay, done. And this particular part is spring. This one is spring, and this one is my pointer. What will happen now? Current will flow. Current will flow through this line and enter this loop. And we know that if magnetic field is present, current is flowing, there will be a torque. What will happen now? Okay, there will be a torque. We know one thing, that sir, if we are having a coil, and in the coil, if my current flows, if my current if my in my coil my current flows through that particular current flowing, I will have my magnetic field. Then that magnetic field will experience a torque, and torque is equals to mb sine theta. Done. Torque is tau. What is m? Magnetic moment. Is it NIA? NIAB sine theta. If you are buying this moving coil galvanometer from a company, number of turners is fixed. It is a part of the instrument. Area is also fixed, and it is magnetic field, because these two things are fixed. So it is fixed. Now you can see my torque, that means the rotational thing of my coil depends on current and my theta. So it is very difficult for us. So we fixed this theta also. How? Every time we need to get 90 degree. That's why we placed these cylindrical magnets. Use of cylindrical magnets is only that it should give 90-degree angle. So now place the values. Torque came out to be NIAB sine 90 degree. Sine 90 is 1. So torque came out to be, it is NIAB. So N constant, A constant, B constant. Therefore, I can write torque is proportional to current. So which simply indicates if you are having more current in the coil, there will be a more deflection. Okay, more current in the coil, more deflection. That is more torque. Done. So can I write here? more current, more current, more deflection, more deflection, more deflection. Okay. Now, what is the use of this spring? What is the use of the spring? When this coil is rotating, I need to stop, na? I need to stop this coil. Okay, if let's suppose it is going in this way, so I need to stop it here only. Okay, so this coil, this spring is providing the restoring torque. Restoring torque, like the spring behind our doors at our home. What is the usage of the spring behind the door? It prevents further movement of the door. The same way, this restoring torque, this spring produces restoring torque, which prevents this rotational elongation of my loop. And this thing, my restoring torque is proportional to deflection. What is this phi? Phi means deflection of coil. Deflection means rotation of coil. More rotation, more deflection, more restoring torque. Here is proportionality. So can I write now this tau is equals to some constant C into phi. C came out to be, it is torque by phi. Done. What is torque? Is it NIAB? Yes, sir. It came out to be NIAB by phi. Remember this thing. Now at equilibrium. At equilibrium. Net torque should be 0. Can I write now? Can I write now here? Deflection torque. Deflection torque equals to my restoring torque. Okay. So what is my deflection torque? Is it NIAB? Yes, I will write here. It is NIAB. Restoring torque is C phi. So from this particular thing, what I can get? C also, right? So C came out to be NIAB by phi also here. Same, no? Same. Done. Now, after this thing, we are having sensitiveness or sensitivity of galvanometer. It is sensitivity. Sensitivity of galvanometer. Galvanometer. Sensitivity of galvanometer. First sensitivity means current sensitivity. Current sensitivity. Second one is voltage sensitivity. Voltage sensitivity. Current sensitivity means CS. C current, S sensitivity. It is deflection per current. Deflection per current. Voltage sensitiveness is deflection per voltage. Deflection per voltage. Now you can see here. Look now. Deflection is phi. Current is I. Deflection is phi. Voltage is V. Or you can write phi voltage is V. It is I into R by Ohm's law. Okay. One more thing. CS. Current sensitiveness. What is phi? What is phi now? I guess phi from this particular equation I will get my phi. So phi came out to be N I A B by C. So can I write here? It is N I A B by C whole divided by I. I cancel out. So my answer came out to be N A B by C. This one, voltage sensitiveness, it is phi. Phi is NIAB by C whole divided by, it is I into R. I cancel out, so my answer came out to be NAB by CR. By CR. Now, based on the sensitivity of the galvanometer, we are having a one numerical, simple numerical. Numerical is like, if we double n to 2n, if we double this thing from n to 2n, find effect on CS and VS. Let us talk about firstly for CS. CS, I guess it is NAB by C. Now we double n, it will become 2NAB by C. That means CS doubles. CS also double. CS double. Now if we talk about VS voltage sensitivity, it is NAB by CR. N is 2n now. Is it 2n? AB by C. What about the R? I guess R equals to rho L by A. If we increase the number of terminals increases the L. And if we increase the L, R will increase. That simply indicates, if we are increasing N to 2N, so it will increase L to 2L. It will increase R to 2R. So can I write now here, instead of R, I will write 2R. 2 cancel out, so VS came out to be the new one. It is NAB divided by CR. So I guess these are similar, no? So no effect. So no effect. Am I not visible? 1 second, I will check it out. 1 second, beta. Don't worry about it. Am I visible now? Am I visible now? Yeah, I'm visible now. Okay. 1 second, 1 second, 1 second. Now I'm visible now. Okay. So I guess we are done with this particular case now. So we complete this one. Now let us start new topic known as magnetic materials. Okay. Magnetic materials. Magnetic materials. First thing that we need to study from this particular topic, that is atomic magnetization. That is atomic magnetization. Atomic magnetization. It simply indicates that if we are having an atom and in my atom, electron is revolving. This is my electron. This electron is revolving with some speed v. A radius of this atom is r, or small r or capital R. No issue, right? No, I will write small r. Done. Now, what is the speed? I guess one thing we know, that speed equals to distance by time. We know this particular equation from 9th class. Speed is v, distance is 2 pi r, circumference of the circle divided by time is t. Therefore, time to cover the whole circumference is 2 pi r by v. 2 pi r by v. If this electron is flowing, due to this flow of electron, we will be having a current now opposite to it. So this is my current I. Current I will flow in this manner. 1 second. So it will not be in this way. My current will flow opposite to it, that is I. So how to write I? Sir, I is equals to charge per unit time. Charge means electron is flowing. Time, we know it is 2 pi r by v. So my current came out to be EV divided by 2 pi r. So this is the equation of current if my charge is moving. Easy beta? If we want to find out magnetic field at the center, okay, if we need to find out magnetic field at the center, I guess we know it from the Biot-Savart Law, no? That is B equals to nu naught current I divided by 2 times R. Nu naught by 2R is same. What is I? I is, I guess, V EV divided by 2 pi R. Okay, so I can write this nu naught EV whole divided by 2 to the 4. It is 4 pi R square. This would be my magnetic field at the center of this Bohr orbit. Look now, this is my equation now. Simple. So look now. So I guess my B came out to be, it is nu naught EV divided by 4 pi R square. Yes, sir. Can I write now R square is equals to nu naught EV divided by 4 pi B? Okay, so look now, nu naught constant, this is constant, charge is constant, 4 constant, pi constant. So therefore, I can write R square is proportional to V by B. So R is proportional to the under root of V by B. This particular thing was asked in your NEET examination. This is NEET PYQ. This particular thing was asked in your NEET. Okay. Okay. In the same slide. What to write? What is magnetic moment? M is, it will be current into area. What is current? Is it EV divided by 2 pi R? What is area? Is it pi R square? Yes, sir. Pi cancel out. R cancel out. Is it EVR by 2? Or you can write 1 by 2 EVR. 1 by 2 EVR. It is magnetic moment now. So if you need to write magnetic moment due to orbital motion of electron. Orbital motion of electron. Done? Clear? Huh? Clear beta? Easy or super easy? Okay. So, okay, one more thing. Diagram. Okay, so let us end this session here only. So rest thing. Daksh, I guess you were present in yesterday class also, no beta? If I'm not wrong, no, Daksh. Okay. So what we can do now? Tomorrow we will start. Tomorrow will be the last class. Then from Friday we will start. I guess from Friday, no? Look, today is Wednesday. Yeah, from Friday we will start EMI. Okay, great. So tomorrow maybe that lecture will be somehow lengthy. I will stop now, okay? Because we study many things in this class. So I don't want you to just get a pile of concept in your mind. So just watch this lecture, enjoy these things, make your proper notes. And from today we will be starting paramagnetic what are the ferromagnetic things, okay? What is magnetizing things, what is intensity of these things, right? So tomorrow most probably we will end the whole lecture series. And if you have any confusion or if you want me to let know anything, so you're most welcome. You can just ping me a message and we will be having a great discussion, okay, on that particular thing. Don't worry about anything, right? So I hope you enjoyed this session. If you have any confusion or if you want to ask me anything, you can just let me know. Okay. We are having Sobia car, JEE NEET rally. Okay. So is there any do I need to just give you any answer for your these things? Okay, first of all, you are this. I don't know why you are just saying this, no? Thank you, Beta. Thank you very much. Okay, so thank you. Good night. Bye. Take care. Okay, no worries, Beta. I'm not here for you, no? Thank you, Beta. Bye. Good night.